Okay, in this video we're going to be applying the concepts that we learned in the previous two videos, and we're going to analyze a beam that has several distributed loads on it. So the first thing we gotta do is we gotta figure out what the resultant forces are for each of these distributed loads. So in this case, for example, we have a rectangle, so that's an uniformly distributed load, which means the resultant force is going to be in the middle. In this case, the total length of this section is going to be 2 meters. That means it's going to be located at 1 meter from the left. And the resultant force is going to have a magnitude equal to the area. So in this case, the height is 6 kilonewtons per meter. The width is 2 meters. So that's 6 times 2, which is 12 kilonewtons. And that's essentially what we're going to have for that first section. Then for this central force, that's a point load, which means that we don't need to worry about it. It's already its own resultant force. For this one, however, we have to use integration because it is given as a function in terms of x. Now in this case, what we notice is that even though we're starting off this not at the reference point here, but rather somewhere here in the middle, we don't actually need to use this as the reference and set it equal to x equals 0. In this case, we can just look at this distributed load by itself, so we can just isolate it from the rest because we know that the resultant force is only dependent on the area. So we have 2x squared, that's the function we have. Now we're going to choose this point over here as a reference point, x equals 0, and then this point over here at the end is just going to be x equals to 3.5. So now the first thing is the resultant force is going to be equal to the area, which is the integral from 0 to 3.5 of 2x squared dx, which is going to be the integral. So that's going to be 2x cubed over 3 from 0 to 3.5. And now if we plug in 3.5 into this formula, that's going to be 3.5 cubed, so 3.5 cubed divided by 3, which is about 28.58 kilonewtons, because the next one is just 0. So that's going to be the resultant force in this case. Now the next thing we're going to do is we're going to calculate the centroid, or the location of this force from the left. So let's call this x bar. This is the location of the centroid. So we know that this is going to be equal to f1 over fr. And this is going to be from 0 to 3.5 of x times 2x squared dx. So in this case, we have 1 over 28.58 of 0 to 3.5. And now we have 2x cubed dx, which means that we're going to have 2 divided by 28.58. Over here we're going to have x to the power of 4 divided by 4, and that's going to be integrated from 0 to 3.5, which is going to become 2.625 meters from the left. So now that we have all this information, we can proceed and draw the Freebody diagram for the whole structure. So this is what we're going to have over here. So reaction at A, reaction at B, and then over here we're going to have our reaction force for the rectangular load, or the distributed uniform load. That was calculated as 12 kilonewtons, and it is located at 1 meter from the left hand side. Then somewhere over here we have a 3 kilonewton load, and this is essentially located at 1 meter from here. So basically we have 1 meter here, 1 meter there, and now we have 0.5. Now here we have our distributed load that looks like a parabola, But the resultant force of that is located somewhere over here, which is, as we calculated, at 2.625 meters from this reference line, and it has a magnitude of 28.58 kilonewtons. Now the total length of the beam, and this is important to know, is going to be 3 plus 0.5 plus 3.5, so that's going to be 7 meters. So this is going to be important for when we're doing the sum of the moments about A. Alright, so now we can proceed and I forgot to mention that we have RAX equals to 0 because there are no horizontal forces on the system. Okay, so next thing is sum of the forces in the y direction. That's equal to 0. In this case, we notice we have minus 12, minus 3, minus 28.58. And then we have RA and RB. So that means that RA plus RB should be equal to 43.58. And then we're going to do the sum of the moments about point A. So let's do it over here. Let's assume this is positive. Sum of the moments about A. And now the next thing is going to be, so we're going to have the first force is occurring at 1 meter here, and it is rotating clockwise. So that's going to be 1 times 12, which is just 12. Then the next one is going to be located at 3 meters from the reference point at A, and that has a magnitude of 3, so 3 times 3. And then the last one is going to be 28.58, and that's located at a total distance of 3.5 plus 2.625, which is 6.125 times 28.58. And then we have the last one, which is RB. That's going in the opposite direction, so that's going to be minus 7 RB, which means that RB is going to be equal to 28.01 kilonewtons. And that implies that RA is going to be 43.58 minus 28.01, which is equal to 15.5725 kilonewtons. And those are our two answers. So hopefully this video has helped you understand the concept behind distributed loads and how we can actually combine them when they're basically different on the same structure, and we can use those concepts of resultant force and centroid to essentially compute those equivalent forces and moments.